All right. So, welcome to the webinar 11 for year 12. Today's topic is energy, work, and power. Okay. Now, let's look at the first problem, and it's very similar to the one that is given in the assignment. So, in general, questions today are very similar, actually. So, yes, if you stay, you will benefit a lot from today's session that will help you with an assignment, definitely. Okay, so a person is standing on ice and pushing a cart of mass m. Okay, so the person is pushing, and there's a cart. So whatever that is, maybe it has wheels, maybe it doesn't. The person is standing on ice, so it doesn't really matter if there are wheels or not. Okay, so now because there's a force, the first person pushes with the force, and the cart moves as a result of that force. That means work is being done, because work is force times distance. So the person is doing work on the cart. Person doing work on the cart. As a result, the kinetic energy of the cart increases. Because when you do work on an object, its kinetic energy will increase. Kinetic energy of cart increases. So if I take a ball, for example, if I take a ball and I apply a force, so I push it and the ball moves as a result of that force, I'm expecting the ball to have kinetic energy after I've pushed it, right? Or if I hit it with a bat, I apply a force and the ball moves as a result of that force acting. Therefore, I have done work on the ball, and that means that the ball has now kinetic energy. And by the work energy principle, work energy principle, the work done is equal to the change in kinetic energy of the object. So if I do 10 joules of work on the cart, that means the cart now has 10 joules of kinetic energy. Of course, there might be friction, so you have to consider that as well. So you're doing work on the cart, but also friction does negative work on the cart, and that's why you don't always have that that the work done by you is kinetic energy, because maybe another force is doing work, maybe friction is doing work. Friction can do negative work, so it's taking away energy. So let's write that down. This is not the case, but friction does negative work. So work is less than zero, and that means that the change in kinetic energy is less than zero. And when you look at it that way, it makes so much sense. Friction does negative work, and work is change in kinetic energy. So if the work is negative, the change in kinetic energy is negative. That means the kinetic energy is decreasing. I don't know. I find that fascinating. Now, why does friction do negative work? Well, because if you have a mass moving to the right, so it has velocity to the right, that means the frictional force is to the left. Force of friction is to the left, but the movement is to the right, so the displacement is to the right. And work is force multiplied by the distance multiplied by the cosine of the angle between the two vectors. And in this case, this angle is 180 degrees. So because you're moving one way and the force is another way, so there's 180 degrees and cosine of 180 degrees. So it's Fs multiplied by cos 180, and that is minus Fs. So it's less than zero. Well, modulus F, modulus S, modulus F, modulus S. Yes. Actually, work is the scalar product of the two vectors, right? So work is actually F dot product S. If you didn't know that before, then now you do. Brilliant. So, this is like an intro. This is an intro to the topic. So I'm not exactly solving the problem at the moment, but person pushes the cart. Work energy principle says the work done is the change of kinetic energy. All right, cool. Now let's go back to the actual question. So the person has a mass m. Why would we need the mass of the person? Like, does anyone know why would we need the mass of the person? Like, does it really matter? Right. And yeah. Well, because the person has no friction either. So according to Newton's third law, if the person pushing the cart, that means the cart is pushing the person with an equal but opposite force. So man pushing, is it a man? Person. Sorry, being presumptuous. Person pushing, person pushing cart, cart. And this is cart pushing person. Okay. But that means if there's a force on the person, that means work will be done on the person. So work done by cart on person. As long as the person is allowed to move. But the person is allowed to move because they are standing on frictionless ice. Therefore, if you push someone standing on ice, they will move. So kinetic energy of the person increases as well. Increases. So actually, work done by person is equal to the change in kinetic energy of the cart plus the change in kinetic energy of the person. Because because they are pushing themselves against the cart, so and moving backwards. Okay, so that's conservation of energy for you, or the work energy principle for you. But the rest is actually quite easy. Okay, so we have a cart of mass m small and the person of mass m big. And the cart is moving away at velocity v, conservation of momentum. The person must be moving to the left with speed u. So, conservation of momentum. Before the collision, so 0, so they were both stationary initially, equals minus mu, because they're moving to the left, plus mv, the cart is moving to the right, and therefore mv is mu. That's an explosion. This is a model of an explosion, and we say that the speed of the person is mu over m. What do we need to find? Find the speed of the person immediately after the push. Oh, we found that u is m over m times v. Okay. Calculate the total work done by the person doing the push. Okay. So that's A. B. So the kinetic energy of the cart is going to be 1/2 mv squared. Kinetic energy of the person is 1/2 capital M multiplied by u squared, which is 1/2 capital M times m squared u squared. So that's V. What? Sorry, messed up. MV divided by capital M. So that's M times M squared multiplied by V squared divided by capital M squared. This cancels, which is 1/2 M over M. Well, M over M multiplied by 1/2 MV squared. I'm writing it like this because now we can see that they are corresponding. Well, they have the same expression. They contain the same expression. So total work done. So total work done is kinetic energy of the card. Kinetic energy of the card. Well, the change in kinetic energy of the card. Change in kinetic energy of the person. Plus change in kinetic energy of the person. Well, you don't really need the change because it starts from 0 and ends with some kinetic energy. So the change is equal to kinetic energy. So the change in kinetic energy of the card is 1/2 mv squared plus m small m over big M times 1/2 mv squared, which is 1/2 mv squared, open bracket 1 plus m over m. Okay, so that's the expression, and then explaining the work is not equal to the final kinetic energy of the card alone. Well, yeah, we've explained that, right? So some of the energy goes into the card, some of the energy goes into the some energy goes into moving the person. Okay. Um, Energy used in a stop-start driving. Now, when you drive a car, energy is used to accelerate the car to get it to speed. But once the car is at speed, energy is actually only used to fight air resistance. If you think about it, the work done is equal to the change in kinetic energy. So once you got the car to speed, you don't need to change its kinetic energy anymore. Right? So if there was no air resistance, you wouldn't need any fuel to keep moving. You can imagine that, like in space, like the Voyager space mission. It launched in 1977. It had a very little fuel on board, and it's used up all its fuel by now. But it's still moving. Still has massive kinetic energy, something ridiculous in the rounds of 50 kilometers a second, plus or minus 20. I don't remember the actual number, but it has lots of kinetic energy because there's no friction, right? So it was launched in 1977, and it's still moving. It's past Pluto, and it's somewhere in the outer solar system, in the approaching the Kuiper belt, or in the Kuiper belt. Don't quote me on that. Yeah, so once the car is moving, you only need fuel to fight the air resistance. So once the car is at speed, then the change in kinetic energy is 0. So work of engine is only to compensate compensate for the negative work done by friction. The negative work done by friction and air resistance, of course. Let's say air resistance. Resistance, because this is by far the biggest force. I don't know if you've ever thought about cars in that way, but yeah, that's how it is. You use fuel. That means you use work. The engine does work, but that work is only to maintain your speed. But if you go start, stop, start, stop, start, stop, then every time you start, the engine does lots of work accelerating you. Then the brakes do negative work decelerating you. Then again, you have to accelerate again. So you're using much more energy if you start and stop the car. When the car stops, when car brakes, the brakes do negative work, negative work, stopping the car. The car. Once again, work is change in kinetic energy, and the change in kinetic energy is negative, so work is negative. It makes perfect sense. All right, so a car repeatedly accelerates from rest to speed. So, A, work done by engine in one cycle, and that's equal to the change in kinetic energy of the car, which is 1/2 mv squared. It travels a distance s and then brakes to rest. Okay. The time it takes to time to accelerate, right? Time to travel. No, assuming the acceleration is fast. Time to travel a distance s. S is t equals s over v. Now, I'm making a huge assumption here. I'm assuming that the speed is constant. So I have to mention that assumption. Assumption S is significantly larger than the distance needed for acceleration. So we're assuming that the speed of the car is constant effectively. So what are we saying? I'm saying that the speed and time goes like this. So the speed quickly goes to maximum. Speed quickly goes to the desired speed, and then it's constant for some time. Then it quickly decelerates, and then quickly accelerates, and continues in that fashion. Start, stop, start, stop. Okay. So what I'm saying is that the time, this time to stop and start is very small. Small time. And in that way, we can assume that the car is approximately a constant speed. Right. The speed of the car can be assumed to be constant. You have to make assumptions when you're dealing with physics problems. Everything, not always, and not everything is very well defined. So yeah, especially in estimation questions. All right. So this way, I'm ignoring the time it takes for the car to accelerate and the car to decelerate. Right. So what does that mean? Uh, the car repeated loop finds the average power dissipated by braking. Well, work done by engine in one cycle. Work done by brakes to stop the car, and that's the important bit. Work done by brakes to stop car. Well, isn't that just the change in kinetic energy? Change in kinetic energy. So that's just negative 1/2 mv squared. Right? The brakes are making negative the same amount of work as the engine. So the engine does work, and then the brakes do the exact same amount of work, but removing energy from the car. So the engine adds energy, tops up the energy, and the brakes just take that energy away and dissipate it as heat, of course. Okay. And then in one stop. So work done by brakes in to stop the car. B. Power is work divided by time. So, and because the car stops every S over V seconds, car stops every S over V, T equals S over V, T equals S over V seconds, then we can find the power. Power is work divided by time. So it's 1/2 mv squared divided by time, which is S over V, which is mv cubed divided by 2s. That's the expression for power. Explain quality of how increasing the distance between stops affects fuel efficiency. Well, it reduces the power if S increases. So C, if S increases, you can see that the power is inversely proportional to S. So power decreases. If S increases, power decreases. And that if the power decreases, that means the amount of fuel needed decreases, and therefore efficiency increases. Efficiency increases. Although efficiency of a car is not very well defined. How do you define efficiency of a car? Because efficiency is how much energy well is the kinetic energy of the car. So how much energy goes into the car divided by the total work done by the engine, right? But what is efficiency? So this is of course there are different ways to define efficiency, but and efficiency doesn't always make sense because if you just follow the definition, so what is efficiency? But what do you mean? You mean by efficiency? See, usually efficiency, and C, which is the Greek letter eta. Eta is efficiency, and that's change in kinetic energy of the car divided by the work done by engine. Work done of the engine. But if the car starts with 0 joules of energy and ends with 0 joules of energy, you see what I mean? So if the car starts at 0 meters a second and finishes at 0 meters a second, then that's just 0. So the efficiency is 0. Well, By that metric, efficiency of any car is zero because it starts stationary and finishes stationary. So they changing kinetic energy is zero. I don't know. It's a philosophical question. You normally talk about the efficiency, of course, is the work done against air resistance divided by the well, yeah. When you're talking about fuel efficiency, you normally say um, how far you can travel on a given amount of fuel. So if that is what you mean by efficiency, it increases, of course. And efficiency increases and fuel efficiency increases. So efficiency in the strict definition and fuel efficiency are different things. Okay, so but it's not always obvious what you mean by efficiency. Okay, so let's put it this way. But I think efficiency of a car, efficiency of a car is very low for many reasons. I think cars are not really good because they take so much space. They're so inefficient, right? I am a very much advocate of bicycles and the buses. Anyways, well, today we are covering energy work, power, and energy, work, and power. Okay. Diminishing bounce heights. The ball is dropped vertically from a height h0 on a rigid surface. Every time it collides with the ground, it loses a fixed fraction of its kinetic energy. All right, so if it starts with h0, so it bounces off the ground. Second bounce is to a lower height, lower height, lower height, etc. And it starts with h0. So when the ball is at the top, ball at top, then the gravitational potential energy of the ball is mgh0. Ball about to hit the ground, of course, it now has kinetic energy. And the kinetic energy is equal to the gravitational because there's a conversion from gravitational to kinetic, so mgh0. So when the ball is about to hit the ground for the first time, it has mgh0 of kinetic energy. Now, if you bounce the ball up now this way, when it bounces, its kinetic energy will after first bounce, the kinetic energy is now F mgh0 at the top of this bounce. So this is mgh0, this is F mgh0, this is F squared mgh0, etc. F cubed mgh0. And you can see that the height of the bounce every time, so this is h0 is h0. h1, the first bounce is f h0. No, it loses a fixed fraction. It loses a fraction, so it's 1 minus f. Okay. No, it's 1 minus f. 1 minus f squared, 1 minus f, 1 minus f squared, 1 minus f cubed. h0, this is 1 minus f h0, 1 minus f, so h2, this is the height of the second bounce, squared h0, the height of the third bounce H3 is 1 minus F cubed H0. Find the height reached after the first bounce. Okay, first bounce, A. This is F, 1 minus F times H0. After the nth bounce, so first bounce, second, that would be 1 minus F to the power n H0. Determine how many bounces occur before the first, because the height of the ball force below H0 over 10. Okay, so 1 minus, so C. So 1 minus F n multiplied by H0 is less than H0 over 10. So 1 minus F to the power n is less than 0.1. So n is, this is an inequality. This is an exponential inequality, and the base of the inequality is less than 1. Okay, 1 minus F is less than 1. 1 minus F is less than 1. So it has to be, we change the sign. So n is greater than logarithm base 1 minus F of 0.1, and whatever that F is. So we don't know F, so that's the answer. Okay. All right. Number 3. Number 4. Sliding on an elevated ramp. A small block slides without friction down a straight ramp inclined at an angle alpha to the horizontal. So we don't know, we only know the height of the ramp, and we don't know that angle. Okay. Find the speed of the rock at the bottom of the ramp. I'm going to do it. I'm going to do it in a tedious fashion, slightly tedious. So we have a block, and it has a mass m. Let's consider the forces acting on that mass. And there's, of course, the mg force. There's the normal force, normal reaction force, and there's no friction. So those are the only two forces. Now the displacement of the block is this. This is the displacement of the block, S. This is S. So we have mg is a vector, n is a vector, and S is also a vector. Okay. Now, how tedious do I want to get? Do I want it to get? Okay, I'll make it very, very bad. But bear with me. I'm going to use column vectors because why not? Using column vectors. Right. So mg, the weight mg is a vector. It can be written as 0 minus mg. Right, so it's 0 to the right and mg downwards. Okay. The normal force, it has two components. It has two components. It has n, this is alpha, n cos alpha, and n sine alpha. So n can be written as n cos alpha, no, n sine alpha, n cos alpha. Okay. And the vector S, So vector S can be broken down into two components. That's the vertical component, Sy, and Sx. But we know that the vertical component is just h, well, minus h. So S is minus h downwards. And to the right, that's going to be h. If this is h, this is h over tan alpha. H over tan alpha. I believe so. Let's check. Tan, if this is alpha, so tan alpha is Sy over Sx, yes. And Sx is going to be Sy over tan alpha, which is H over tan alpha. Okay. And then now I want to find the work done. So we're using work energy principle. And I repeat myself. This is a very unconventional way of doing it. So don't get me wrong. You don't normally do things like that, but I can show you that even doing it this way, you will obtain the same answer using work energy principle. Work is the change in kinetic energy. So the change in kinetic energy of the block is equal to the work done by gravity plus the work done by the normal force. Work done by gravity by the work done by the normal force. So, and we know that the work is force times the displacement. So work done by gravity is force of gravity multiplied is a vector multiplied by the displacement of the block. So the block moves. So what we need is we need the gravitational force. So 0 minus mg multiplied by the displacement. So it's h over tan alpha minus h. And we know the scalar product of two vectors, we just multiply them. So it's 0 multiplied by h over tan alpha plus minus mg minus h. And the answer is mgh. Who would have known? The work done by gravity is mgh. Okay. It looks like I've just invented the bicycle. But anyways, do you understand how I did that? Did you manage to follow the whole explanation? I've written the force and the displacement as column vectors, and then just multiplied them to get the work, because work is just the product of a force times displacement. So work is force multiplied by displacement. So I took this vector and I took this vector and I multiplied them together. So yeah, do you understand? Give me something in the chat. Tell me something. Was that easy to follow, or did you get lost in the explanation? Anyone? Sure. Okay, understandable. Good. I've got one person replied. Now I want to find the work done by the normal force, because there's another force doing work, presumably. Work done by the normal force is the normal force multiplied by the displacement, and that's going to be, the normal force is n sine alpha, n cos alpha, multiplied by the displacement, which is h over tan alpha, minus h. And this is going to be n sine alpha multiplied by h over tan alpha minus n cos alpha times h. And this is going to be n sine alpha h over sine alpha over cos alpha. So sine alpha cancels and cos alpha h. And then you can see that n is going to be nh cos alpha minus nh cos alpha, which is 0 joules. And it is. It's the work done by the normal force is 0. Why, how does that make sense? Well, because the normal force is at a right angle to the displacement. Right? The angle between the normal force and the displacement is 90 degrees, so the work done by that force is 0. Okay, so the change in kinetic energy, of the block is equal to mgh. That's a very, very long way of doing it, but hopefully that makes sense to you. The speed, and we know that the kinetic energy is 1/2 mv squared. Mv squared is mgh. M cancels, and we have v squared equals 2gh square root 2gh. So v is equal to square root of 2gh. That's the speed of the block at the bottom. Speed at the bottom. At the bottom. Speed halfway. That's A. B. Speed halfway. Well, you can use energy conservation now. I mean, do it the simple way. Conservation of energy. Conservation of energy. So you have alpha. And oh, by the way, you can see that alpha cancels out. Even though alpha is present in the expression, note, answer does not depend on alpha. It doesn't matter. The angle doesn't matter if the angle is steeper or less steep. Only the initial and final height. Conservation of energy. So now when you for this situation, halfway down the slope, then this is h over 2. So the amount of energy. Okay, let's make it proper. Let's do it properly. So at the top, we have kinetic energy is 0, and gravitational potential energy is mgh. At the middle, kinetic energy is 1/2 mvm squared, middle. Like middle, v1 squared. And the gravitational potential energy is mgh over 2. It's half. Kinetic energy is half. So, and we know that the conservation of energy at the top, total energy at the top is equal to the total energy at the bottom. And therefore, 0 plus mgh must equal to 1/2 mv1 squared plus mgh over 2. So 1/2 mv1 squared equals mgh over 2. 2 cancels, m cancels, and v1 is equal to square root of gh. So halfway down the slope, the speed is square root of gh. So square root of 2 times less. And explain why the result does not depend on the angle alpha. Well, Well, you could see that. You could see that from this expression. It does not depend on alpha. Another way, well, just from the conservation of energy. Like this is, I've actually given two reasons. So I'll just write C above. Above. Okay. Spring-powered launcher. A ball of mass m is launched by a horizontal spring of spring constant k. The spring is compressed by a distance x and then released. So we have a spring that is compressed by a distance x. So x is the compression. So that would be this distance. This distance. The x is the compression. Compression. So it used to be here. Now, when you release it, it will fling to the right. Now, the speed of the ball. So the spring constant is k. So the energy you have energy. So elastic potential energy of the spring is 1/2 kx squared, and once it leaves, so the because elastic potential energy goes into kinetic energy, which is 1/2 mv squared, and therefore 1/2 kx squared mv squared, and v is equal to k over m square root multiplied by x. That's the speed of the ball when it leaves the spring. Speed of ball. Now, if the same setup is used vertically, find the maximum height reached. Okay, so here's slightly more tricky, because when you maximum height above so this is the unstretched spring. This is the neutral length of the spring. This is the ground. Now, when you place the ball onto the spring, the ball will move down. So this distance is x. And once you reach from unstretched spring, when you place the ball, and when the stretches, the ball flies up with some speed v, and then finally the ball reaches maximum height. Now, the problem is, where do we count the maximum height from? I would say we count the maximum height from the unstretched position. Right? Or do we? Well, I don't know. Maybe not. No, let's measure the maximum height from the lowest position. This is the maximum height. Yeah. And we just place three different well, no, three different positions. So position 1, the spring is compressed. Position 2, the spring is not compressed, and now the ball is flying. And position 3, the ball has reached maximum height. And now we need energy in position 1. In position 1, So the ball has no gravitational energy. Gravitational potential energy is zero. Kinetic energy is zero, and elastic potential energy is equal to 1/2 kx squared. In position two, gravitational potential energy is mgx. In position, kinetic energy is, well, 1/2 mv squared, which we don't know, and elastic potential energy is zero. And in position three, we have gravitational potential energy is mgh capital, kinetic energy is zero, and elastic potential energy is zero. Okay, so comparing 1 and 3, so 1 equals 3, we have elastic potential energy 1/2 kx squared equal mgh. And in this case, h is equal to kx squared divided by 2mg. Lovely. So that's the answer to question B. And the question 3, C, asks, compare the energy transfers in the horizontal and vertical cases. So what do they mean by that? Well, actually, we want to know the speed at which the ball leaves the spring. Speed at which ball leaves spring. And that speed, well, we need to compare 2 and 1. So 1/2 mv squared plus mgx equals 1/2 kx squared. And you can see that, well, you can multiply by 2, so v squared equals kx squared minus 2 gx divided by m. So v is equal to square root of kx squared by m minus gx. Have I made a mistake? No, I don't think so. And you can see that this is less. This is going to be less than the horizontal throw, less than square root of k over x, k over m times x. And that means that the vertical throw would be less. Vertical throw is less because some of the energy of the spring is used to raise. So vertically, ball leaves spring with a smaller speed. This is due to the negative work done by gravity, right? As the ball rises, that small amount of x, as the ball rises through x, a small distance x, the gravitational force does negative work. Gravity does negative work, reducing the speed, Okay, so quite interesting thinking that way, thinking about forces doing work. Okay. I've got 3 very interesting questions. And I really hope to get to the end. Train climbing a gradient. The train of mass m travels up a straight incline at speed v. So train mass m, speed v. The engine provides a power P, and the resistive force is proportional to the weight of the train. So there's a resistive force which is K multiplied by mg. Find the expression for the maximum angle the train can climb at that speed. So the angle is question mark. Okay, so obviously the engine is producing a force F, and it's going at the speed v. So power from engine is equal to Fv. So Fv. So the force from engine, F, is equal to power divided by V. So the force needed is power divided by V. And because it's going up at a constant speed, then we have F, the gravitational force, so it's mg, and you can break that into two components. And so this is mg sine alpha. So mg sine alpha. So the forces along the slope, forces along slope. Then we have the force forward, the forward force must equal to kmg plus mg sine alpha, and F is P over V equals kmg plus mg sine alpha, and from here PV minus kmg all over mg, that's equal to sine alpha. So alpha is arcsine of that expression. So P over mgv minus k. That's the solution. Number 7, accelerating at constant power. Now, number 7, I've sourced this question, and I just realized it matches perfectly the question from the assignment. I'll try not to give away the full answer, but I will give some hints. Well, you know that power is equal to F times V. And a car engine delivers a constant power, and the force that pushes the car forwards. So we have a car, and the force that pushes the car forwards, well, that's the friction in the wheels. That's the force. The force pushing the car forwards. Now, if you just consider this expression, so P is equal to mass of the car times the acceleration of the car. So imagine that this is the only force. So we don't ignoring any kind of resistances. Ma times v times the speed of the car. And you can see that the acceleration of the car is the power divided by mv. But acceleration is dv dt. Acceleration is dv dt. Therefore, dv dt is equal to p over mv. And if you do that, v dv equals p over m dt. You can integrate both sides. Speed changes from 0 to v final, and time changes from 0 to t, and you get v squared over 2 is equal to pt over m, or in other words, v is equal to square root of 2pt over m. That's the function of speed versus time. Now, the problem with that function is that when you attempt to sketch it, so this is the velocity versus time, you will see that it is a graph like this. This is the square root graph. What's the gradient of that graph at 0? When t is 0, the gradient, what's the gradient of that graph when t is 0? Can someone tell me? Just looking from the graph, nothing extraordinary. What's the gradient of this graph at t equals 0? What does it look like? Oh, the gradient is infinite. And that means that the acceleration is infinite, because acceleration is the gradient of the velocity time graph, and that's an impossibility. And you could also see that the gradient is from here, because at t equals 0, v is 0, so a is p divided by 0, impossible. So the force at the beginning, force is not p over v, and therefore at the beginning, force is not p over v. Why is it not? Well, because the wheels slip. The engine delivers power to the wheels, yes, but the wheels cannot sustain that force. The force is too big, right? Because if we draw the graph of force versus velocity, at small speeds, the force pushing the car forwards must be infinitely large, which is not possible. So what happens is, first, you are limited. You are limited with your force is limited. So during the initial phase, so that's an impossibility. This graph would be with no slipping, no wheel slipping, which is impossible. So does that mean static friction is greater than kinetic friction? Well, no, that doesn't mean that. It just means that the frictional force must be infinitely big, which is impossible. Our model breaks down. Our model does not work. So this is not a true graph. So the true graph would be, well, because initially the force would be constant until the wheels stop slipping, and then when the wheels start gripping, the force will decrease with right, constant force while slipping, and then a decreasing, and then force is proportional to 1 over v. So you have two sections of the graph, and the velocity first, because the car, so what happens is the only force that accelerating the car is the friction, and friction when the wheels are slipping is mu mg. Mu mg is the frictional force. So acceleration is going to be mu g, and therefore you would have a graph like this. It's a straight line, vt, and then it will become a curved. So here you have wheel slip, and this is no slipping. So initially, for the first section of the graph, until some time t1, which you need to find, your job, find t1, the moment wheel spin stops, and yeah, obtain the equation for a piecewise function. So first is going to be a linear section, so linear, and then it's going to be curved. So yeah, initially the gradient, because you know acceleration is mu g, because that's the maximum acceleration of a car. Because the car's acceleration is limited not by the engine, but by the tires. No matter how much power your engine has, if your tires do not have the friction, you will not accelerate. That's a very important concept. Right? So when a car manufacturer says, my car has enough power to accelerate from 0 to 100 in 0.2 seconds, well, yeah, you have the power, but you don't have the grip. Like, where are you testing your car? You're testing it on a special track where the friction is artificially increased. Or are you testing your car on an actual road where the friction is limited by the dirt and leaves and water and anything that's on the road? So yeah, it's fun to see those stats for cars. Okay, like a Bugatti goes from 0 to 16 in 1.7 seconds. Well, no, it doesn't. Anyways, it will only accelerate at mu g. That's the limit of the car's acceleration, which is the oh, well, okay. For if you have a large downforce, that can be bigger. Anyways, falling folded rope. Once again, this is a question from the assignment itself, and I'm just going to give some hints on how to do it. This is a type of equation that cannot be. This is where you can get an equation of motion. Aim, obtain acceleration from energy, which sounds bizarre. So you have a rope, which is a heavy rope, which is folded in half. Oh no, it's folded in half like this. One end is fixed. And the other end is released, free. You release and it starts falling. Now the tip of the rope, that's point A, will accelerate downwards. And you need to find that acceleration. And it sounds like it's supposed to be G, but it's not, right? Think of a bungee jumper. Bungee. Is that how you spell bungee? No, bungee jumper. Now, if you have a free fall, free fall, then you only have the gravitational force, mg. And according to Newton's second law, mass acceleration is the force. So mass acceleration is mg. So acceleration equals g. So when you're in free fall, acceleration is g. But now, if you're a bungee jumper and you have all this heavy rope beneath you, so the rope, you have gravity pulling you down, but you also have the heavy rope attached to you. All right, let's find a picture of a bungee jumper. Bungee jumper. Um, oh, I would definitely like to try that. But anyways, bungee jumper. Okay, so if you look at this, you have the heavy rope attached at the bottom that is pulling you down as well. Yeah. And that means your mass times acceleration is equal to t plus mg, and your acceleration is g plus t over m, which is greater than g. So a bungee jumper accelerates with acceleration exceeding g. And that's the case for the free end of the rope. The free end of the rope will accelerate faster because not only it is falling under gravity, but it is being pulled down by the heavy rope. And in order to find that, so you take the conservation of energy. So you take this piece of rope. No, you need to look at what happens when the A falls by a distance of x. Right, so I'm just going to, can I do that? Suppose the free end falls by a distance of x. Now the rope is now longer. It hangs lower. Now if this distance is x, now okay, we need to simplify things. So let's say initially we had a piece of rope like this and a piece of rope like this initially. Now, after the end has fallen, you have the same piece of rope on the left. This piece of rope has fallen a distance x, so that's the distance x. And now this piece of rope is now here. So here you have an additional piece of rope, which is x over 2 here and x over 2 here. So now the total length of rope is the same. But basically, so some of the rope has fallen down. I hope that makes sense. What we need to do is we need to find the center of mass of that rope. So now this is the center in original center of mass. This is the center of mass of the rope initially. And we're going to measure it from, it doesn't really matter where from, but let's measure it from the top. So this is the length of the rope is L, then this is L over 4. The center of mass is initially L over 4 away from the top. Now, the length of this piece of rope, L1, is L over 2 plus x over 2. And the length of this piece of rope, L2, is L over 2 minus x over 2. That makes perfect sense. The center of mass of the first rope Center of mass of the first rope is x1. That's the center of mass of the first rope is going to be L over 2 plus x over L over 4. Oh, x L over 2 over 2. And for the second one, x2 is going to be x plus L over 2 over 2, which is x plus L over 2 minus x over 2 over 2. That's the center of mass of this piece of rope. So this is x1 and this is x2. That's the center of mass. And now we know we need the mass of the rope. So mass m1 is some mu time mu is the mass per unit length times the length times L1 times L over 2 plus x over 2. And M2 is mu L over 2 minus x over 2. All right. So x center of mass of the rope is m1 x1 plus m2 x2 divided by m1 plus m2. Sorry, I'm speeding through this a bit, but there is a similar solution in the assignment. So the mass of the first piece of rope is mu L over 2 plus x over 2 multiplied by x1, so L over 2 plus x over 2 over 2 plus mu L2 minus x over 2 multiplied by L over 2 minus x over 2 over 2 divided by the total mass of the rope is mu L. Okay, mu cancels. 2 goes down here. So x center of mass is equal to 8L. So we can take the 4 out of everything. It's going to be L plus x squared plus L minus x squared. So the center of mass is L squared plus 2LX plus x squared plus L squared plus oh no, sorry. Oh no, 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 no. I've made a mistake. Doesn't make any sense. So x2, I've missed x2 is x. So we need to simplify that. So that's going to be x over 4. So it's 4x minus x. So it's 3x over 2 minus L plus L over 2. L over 4. 3x over 4. 3x over 4. Yes. So that is plus 3x over 2. Okay. So that's slightly different. So it's going to be L plus x multiply L plus x squared plus L minus x L plus 3x. Yes. And that's going to, and that's all over 8L. 2, 2, 4, 4. Yeah. And that's going to be L squared plus 2LX plus x squared plus L squared plus 3LX minus LX minus 3x squared over 8L. Do I get something cancelled? Hopefully. X center of mass is going to be 2L squared 5, 4 plus 4LX minus 2x squared divided by 8L. Right, so, and I think that I have done the hardest part. Now, we have gravitational potential energy. We have gravitational potential energy, change in gravitational potential energy is equal to the change in kinetic energy. But which part of the rope is moving? Well, it's only this part of the rope that is moving. This part of the rope is moving, and this part of the rope is stationary. So we have the decrease in gravitational potential energy, and the decrease in gravitational potential energy is the change in the vertical height of the center of mass. The gravitational potential energy, that's for the center of mass. That's how much the center of mass of the rope has moved down. And that would be x center of mass. So L over 4. So minus L over 4. So it's going to be change in gravitational potential energy is the mu times the length of the rope, that's the mass of the rope, multiplied by the gravitational field times the change in height. And the change in height is x center of mass minus L over 4. And that's the change in kinetic energy. And the change in kinetic energy is 1/2 times the mass of that piece of the rope, and that is L2. So mu L2 multiplied by the speed. So that's going to be v squared. Well, that's easy. Because the whole piece of rope is moving, the left piece is stationary. So the energy, the whole energy goes into that moving that piece. I'm sorry, if I'm a bit rushing here, but hopefully you can review that later. So mu cancels. We got L multiplied by G multiplied by 2L squared plus 4LX minus 2x squared over 8L minus L over 4. And you can see that this actually cancels with this. And that's equal to L over 2. Yes. And that is 1/2 L2, and L2 is L over 2 minus x over 2 multiplied by v squared. Almost done. So L cancels, thankfully. So we got G, open bracket, 4LX minus 2x squared divided by 8 equals L minus x over 4 v squared. We can do that, then multiply this by 2. So 4LXG minus 2GX squared equals 2L minus X V squared. 4LXG minus 2GX squared equals 2LV squared minus 2XV squared. Right. And now, something that you probably haven't seen before, done in physics definitely, you differentiate. Differentiate. So I started with conservation of energy. Okay, it was a very complicated expression for conservation of energy, but I managed to do so. It's the center of mass of the rope goes down, so that's the loss in gravitational potential energy. Center of mass drops. And then the kinetic energy of the right-hand section, right section of the rope falls down. Only one person. Uh, Only one person remaining. Okay, I guess that's a bit too hard. Right. Anyways, let me finish this one. So you differentiate, and so I'm going to be 4L and multiplied by 4LG. These are constants, so times x, and the derivative of x is v. For 4LVG minus 2GV equals, differentiate that is going to be 4LV multiplied by acceleration minus 2V times V squared minus 2x times 2V times acceleration. And now I can finally get the acceleration. So acceleration, open bracket, 4LV minus 4XV equals 4LVG minus 2GV plus 2V cubed. Acceleration is 4LVG minus 2GV plus 2V cubed all over 4LV minus 4XV. And that's the expression for acceleration. I hope I haven't made a mistake, but that's, yeah. That's the acceleration of the tip of the rope expressed in terms of the velocity and in terms of the velocity and x. But how do we get the velocity? How do we know the velocity? Well, we can get the velocity from the second expression. We can get the velocity from here because the velocity v squared is 4lxg minus 2gx squared divided by 2l minus x. That's how you get the velocity. Okay. All right, I'll finish here. I, I hope that was useful. I've done a really hard one at the end. I have done this question before on my previous webinars, so please check out last year's webinar. I'll see you in 2 weeks' time. I believe so. The next session is, let's check webinars. 28 work energy, but next one is 18th of February. All right, see you then.